Hello, today we are going to talk about interference and standing waves. When two things interact, we often call it, well, anything, right? When two things interact, we called it collision in the previous chapters. We called it when two things interacted. We also said that energy is transferred from one to the other, and so on and so forth. When waves interact, we give it a special name. We call it interference. All right? Their waves are interfering with each other. Now, interference can be of two types. One where the waves interacting or talking to each other have their phases lined up, or they are exactly the same looking. Okay, so this, for example, this kind of waves. So they are both looking in phase. Okay, in phase meaning none is lagging the other, not one is lagging behind the other, and like if you consider one point on the crest of this pink wave here, we can look at the same point here on the black curve, and we see that the crests are perfectly lined up. So when they talk to each other, this point will increase or add to that point. And so when these kind of interference happen, we call it constructive interference, because the amplitude of the wave adds up or increases. All right, because they're two same kind of things. If you add one to the other, you're increasing the amplitude. It's like if you add more sugar to an already sweet chocolate or an ice cream, then the sugar level is amplified. But if you say, what happens if you add salt to it? Well, in that case, we would have a destructive kind of interference, because one would try to diminish the effect of the other. So salt would try to get rid of the sweetness in the previous example. Okay? So if waves are lined up like looking opposite to each other, for example, the point on the crest here is lined up with a point on the trough here. Then when two waves like this interacts, then we get a diminished wave, or amplitude of the resulting wave is diminished or decreased. This is called destructive interference. What happens when two waves are exactly lined up opposite to each other, that is exactly out of phase, we call that antiphase. Then they exactly cancel each other out to give you zero amplitude. Alright? This interference of waves has important consequences that we are now going to look at. Besides showing you my bad guitar skills, the point of the guitar playing was to get you interested in physics a bit more, alright? It was not to show off. Because playing guitar or any other music instrument involves a lot of physics, actually. And specifically involves a lot of understanding of the standing waves. If you want to understand or explain the phenomenon of musical instruments, often you would come across this standing wave phenomenon. This standing wave, these are waves that are produced between two closed obstacles. So if you think of the guitar, then you would have one closed obstacle at when tied to the one end of the guitar strings, right, in front of the sound hole, and the other one is attached at the head of the guitar, all right, at the head end of the guitar. So the strings producing waves on it are enclosed between two closed boundaries, one here, one here. When waves are produced in between two closed spots like this, then the waves are not actually going anywhere to going from A to some other point B, right? That's why we call them standing waves, because they start going from one end to the other, but then go to the other end, see nothing, and come back down to the original end again. Okay, so this is how standing waves work. They are formed by reflection, by reflected wave from one end with the incoming wave. Okay, so the incoming wave goes, reflects back from the wall and comes back again. So these waves are actually not going anywhere. They're basically oscillating between two closed ends, hence the name standing waves. They're standing there. Alright, now let's look at a wave that maybe you're forming on a guitar string that has some particular frequency. We want to identify some points on this wave. Specifically, we want to identify the points with zero amplitude. Alright, the points with zero amplitudes, these are what we know as nodes. Okay, nodes are therefore points or places of zero amplitude. Okay, since we are identifying places with zero amplitudes, it's just logical to also identify places of maximum amplitude, right? So places like these are what we call antinodes. These are places of maximum amplitude or maximum displacement from the equilibrium state. Alright, where the medium, the string in this case, oscillates the most, we call those places antinodes. Where the medium oscillates the least, we call them the nodes. Okay, now let's also think about this oscillation when we have reflected waves from the other end. So let's consider this is one of the strings of the guitar. You produce a wave on this end and the wave travels and then gets stuck in this obstacle and then has to reflect back. When it does that, we get some sort of wave looking like this. It so happens to be that this, whenever there is two waves, they interfere with each other, okay, and their interference produces specific patterns. And it so happens that we also have nodes and antinodes that describe the pattern of the interference. Okay, when the two waves are interfering, nodes become places of destructive interference, while antinodes become places of constructive interference. Alright, why? Because we have already established that when waves interfere constructively, they increase their amplitude or they have maximum amplitude, and antinodes are such places where we have the medium oscillating the most. So whenever two waves, the incoming and out and reflected wave, are interfering with each other and producing antinodes, these are places of constructive interference, while places of destructive interference are known as nodes, where the medium is oscillating the least. Okay, these are going to be interesting for our study of various patterns of standing waves. Okay, let's investigate some of the patterns and what we can extract from these. So if you have a wave produced like this, so the incoming wave from one end to the other end in the blue and the reflected wave in pink, then we will have, if the wave looks like this, we say we have the longest wavelength lambda, because we have the longest wavelength lambda since the wave only has, the standing wave produced only has two nodes and no nodes in between. Alright, so the in between we have maximum amplitudes, and whenever the wave looks like this with no nodes in between, we have the maximum or longest wavelength. If you, for reference, look at the full sine wave, if it starts from 0, the length of the string will have completed one full wavelength if you have gone from this end to that end, so a node to another node, okay, and you formed one complete wave, or from a crest to another crest, alright, by forming one complete wave. However, here this is analogous to only this part of the sine wave, right? So we can identify that the length of the string is actually lambda over 2, half a wavelength in this picture, correct? Therefore, we can say that the wavelength in terms of the length is 2 times L. This is the longest wavelength of standing waves produced for anything actually, alright? Because you cannot have any other wavelength that's longer than this, because as we will see, for more and more patterns we will have to introduce more and more nodes in between. Alright, so since we have a wavelength, it's logical to ask what is the frequency, right? Because frequency we know is related to the speed. V equals F times lambda. So F equals V over lambda, correct? And lambda we have just found to be 2L. So F is equal to V over 2L. That is the speed over 2L for this pattern of the wave. We call this the fundamental frequency. The fundamental frequency. Alright? And if you look at this equation, you will notice that frequency is inversely related to lambda. So if you have the longest wavelength for this pattern, this fundamental frequency must be the smallest frequency for the standing wave, right? So you cannot have any frequency smaller than the fundamental frequency. Any frequency after this would be bigger, and any wavelength after this will be smaller, alright? This is also given the name first harmonic. Harmonics is related to music, and this is a physics phenomenon. So that is what I was talking about. If you want to really understand music, then you need physics. Well, not really, but if you're interested in the physics, that's what matters. Now, let's look at another pattern that the standing wave can have. With respect to the previous picture, then we can easily see that this is one full wavelength, right? This full length of the string is producing one full wave. Therefore, the wavelength is just equal to the length of the string. Alright? And since this is the length, then frequency is V over lambda. It is V over L. Alright? Okay? This is called the first overtone, or second harmonic. As we can see that the wavelength is actually smaller than the longest wavelength, the first harmonic wavelength. And let's look at, because the first harmonic wavelength was 2L, while the second harmonic wavelength is L. What about the frequency? The frequency for the first harmonic was F equals speed over 2L. The speed of the medium is constant. If you don't change the medium, the speed doesn't change. But in place of 2L, we now have just L. So the frequency is actually larger than the fundamental frequency, which is logical, right? Because whatever happens to lambda, opposite must happen to the frequency. If lambda is getting smaller, frequency must get bigger. If lambda is getting larger, then frequency must get smaller. Alright? If the standing wave pattern looks like this, then by just looking at it, the wavelength now is, if this was L and that was 2L, then this is just 2/3 L, right? Makes sense just by looking at it. And then frequency becomes 3 over 2 V over L. Alright, so 3V over 2L. So frequency keeps getting bigger while wavelength keeps getting smaller. And if you look at this picture, we have two nodes in the middle, while in this picture we had one node, and in this picture for the longest wavelength we didn't have any. So one node was the first overtone, two nodes would be the second overtone. Alright, so this is easier to remember which overtone you're talking about. And whatever overtone you're talking about, just add 1 to it. Second overtone would then correspond to third harmonic. Alright, whichever one you choose to remember is up to you. Alright, these are just different names given to the same thing. Now we can see a pattern here. We can see that pattern is emerging because frequency looks pretty much just off by a factor 3 over 2, 1 and 1 over 2 of multiplied by V over L, and also wavelength is also some factor multiplied by L in all of these cases. So we see a pattern emerging, and it has been shown that ultimately for any n wavelength, so for any pattern for all harmonics, we have a formula that emerges as lambda n, the nth wavelength, where n can be, for the fundamental harmonic, is you can consider it to be 0. For the second harmonic, you can consider it to be 1, or it's often easier to remember fundamental harmonic n equals 1, second harmonic is n equals 2, third harmonic is n equals 3. That's probably easier to remember. So for the nth harmonic, the nth wavelength is 2 times L over n. Alright, so if you have n equals 4, the fourth harmonic, then the fourth harmonic wavelength would be 2L over 4. Alright, and the frequency corresponding to it, the nth frequency or the nth harmonic, would be equal to n times V over 2L. Alright, so if you have n equals 4, then fourth harmonic would be f4 equals to 4 times V over 2L. Okay, so this is established formula that we use for musical instruments, and the standing waves, we need to interpret them. Alright, and all harmonics are actually related to the fundamental harmonic, because our fundamental frequency, this is also called the first harmonic, because as we can see that the first harmonic was V over 2L, and every other harmonic is something multiplied by some number multiplied by V over 2L, which is the first harmonic. Therefore, that relation is Fn, the nth harmonic, is equal to n times the first harmonic. So the second harmonic frequency would be 2 times the first harmonic. The third harmonic frequency would be 3 times the first harmonic, and so on and so forth. Okay, so every fundamental frequency or every harmonic is related to the fundamental harmonic. Now it's time to check out an example and learn this thing better. The question in the example that we are looking at gives me a violin string which has a length of 33 centimeters, which is just 0.33 meters, and it is under a tension force of 55 newtons because it is held at both ends, providing a tension on it. And the fundamental frequency of this violin string is 196 hertz. Alright, the first question asks up here, what is the speed for waves produced on that string? Alright, so given the information we have, how can we find the speed? Well, we know that speed is connected to frequency, and we know the fundamental frequency of the string. So we can directly use Fn equal to n times V over 2L. For fundamental frequency that we know, n equals 1. Therefore, F1 is equal to 1 times V over 2L, and we solve for V. V is 2L times F1. 2 is a constant, L is 0.33 meters, times F1, the fundamental frequency given to us to be 196 hertz. Therefore, the speed of waves produced on the string is found to be 129.4 meters per second. So pretty fast. Okay, there's a second part to this question now. The second part is pretty simple. It just asks what is the mass of that particular string. We know from previous lectures that for a string, the speed produced on the string is given by square root of the force of tension over the mass of the string by L, the length of the string. We are given all of these informations. We found the speed in the previous part. We want to find the mass of the spring. We know the length, we know the tension force, right? So we just plug everything in. In here, the velocity is 129.4, that is equal to the square root of the force of tension, which is 55 newtons, over the mass of the string over the length of the string, which is 0.33. Alright, as a start, square both sides to get rid of the square root. Then from then on, it's pretty simple. You have 129.4 squared on one side, and on the other side you have 55 divided by the mass of the string times over 0.33, which turns out to be 129.4 squared equals 55 times 0.33 over mass of the string. If you solve for mass of the string by first cross multiplying both sides, then you get the mass of the string to be around 1.08 times 10 to the minus 3 kilograms, okay, or 1.08 grams, okay. Now there's a third part to this problem. Okay, so the third part is basically an interpretation of how chords work or different shapes work when you're holding the guitar string or the violin string in different positions along the fretboard. What you do when you hold the hold in different positions of the fretboard is the fretboard with open strings were connected to one end, the bridge, and then to the head of the guitar, right, or the violin. When you actually press down on a fretboard, then you're not changing the head of the guitar, it is still at this end. What you're doing is you're shortening the length for which the string remains open. So you're actually imposing a bar or a boundary at a different length, alright, at a different position, like this. So now let's look at the question. How far from one end of the string would you have to press the string in order for the remainder of the string to have a fundamental frequency of 300 Hertz? Alright, so basically this is just talking about you holding down a certain position which is not the open position. In open position, the string would look like this. Now you want to find this distance. How far from this head of, or the old boundary, would you have to press down for the remaining wave to produce a fundamental frequency of 300 Hertz? Alright, for the same string. For same string. Same string means that the medium has stayed the same. If the medium stays the same, the speed can never change. So the velocity or the wave speed never changes. So velocity old must be equal to the velocity new. What was the old fundamental frequency? The old fundamental frequency, let's call it let's call the new one F1 prime. Let's call old one to be F1. The old fundamental frequency was 196 Hertz, right? And now the new one, let's just use a different color here. The new one is given to us to be 300 Hertz, okay? We want to know what is this new length that you have to produce L prime to get this frequency from the same string. But in the older length was given to us to be 0.33 meters, alright? So let's go ahead and solve this problem, or at least try and solve this problem. We know that the old speed and the new speed is the same, and speed is given by f lambda. So f1, the old frequency, times the lambda 1, basically the old wavelength, old fundamental wavelength, and the new one is f1 prime, the new fundamental frequency, times the new fundamental wavelength. Now wavelength and frequencies have expressions given to us. So let's just rewrite them here. Lambda n is equal to 2L over n, while Fn is equal to n times v over 2L. Now, using what is given and the formulas up here, we can write F1 lambda 1 by since we know F1, we keep F1 to be 196. And lambda 1 is just 2L over 1, right? So it's just 2L. 2 times the old length, which was 0.33. On the new side, what do we have? We have f1 prime to be 300 hertz, while lambda 1 prime is given by using this equation right here. It is 2L prime over n. N is 1, so it is 2L prime. Our goal here is to find what this L prime is. You can cut off factors of 2 from both sides and then divide both sides by 300, ultimately ending up with a new length of 0.22 meters, which is obviously smaller than the previous length because you hold it. The previous length cannot be surpassed because previous length was for open string, and then you press down somewhere on the fretboard to change the position of the boundaries. All right. I hope this lecture in using standing waves to interpret musical instruments made some sense. Thank you very much.